Hello everybody. I'm here to kind of quickly review the equations for the transverse shear, as well as make a note that, for solid rectangle and solid circle, we don't have to use the shear formula. So you guys remember from the previous video that the transverse shear stress is calculated based on this shear formula here. Tau equal VQ over IT. V is the shear load. Q is called first moment of area. I is, the area moment of inertia with respect to the neutral axis. And T is the width at which the shear stress is acting. But for certain cross-sectional area, for example, for a solid rectangle, which is shown here, if we have a shear load at a section of the beam, we know that the maximum shear stress happens right in the neutral axis, and that tau max can be calculated using this formula, 3/2 V over A. I showed you the derivation in the previous video. So that's much easier than using what? The VQ over IT. So don't waste your time trying to use VQ over IT if you have a solid rectangle. Remember, that doesn't work for a hollow rectangle. In another video, I will show you how you would handle that. Okay, similarly for a solid circle, it was shown in the previous video that for if you have a shear load acting on a section of the beam on a circular section that is solid, the maximum shear stress again happens right in the along the neutral axis, and it's equal to 4/3 V over A. So then you use this formula. All right, much easier. Remember, this one is shown in the textbook, but this equation actually is not derived in the textbook. So that makes it much more useful to use this equation. All right, let me show you a quick example now. So I have a very simple beam here, a simply supported beam with a uniform load of 1,000 pounds per foot over 6 feet. Okay, and what I want to calculate, I want to actually have two cross sections, one solid rectangle and one, what if it was a solid circle with the dimensions given. So what we need actually, and to calculate, so our objective is to find tau max, the maximum transverse shear stress. That's what we're trying to do, to find. Okay, so first of all, you know that there is the equivalent concentrated load in the middle is going to be 1,000 times 6. That's 6,000. Because of symmetry, you divide it by 2, so the two reactions become 3,000 each. A quick shear diagram, even though, by inspection, you can tell that the maximum shear is going to be 3,000. By the way, when it comes to maximum shear, guys, unlike moment that we have to worry about both positive and negative moment, maximum shear is the absolute maximum shear. So if you had a 3,000 positive and minus 4,500 negative, you will pick the minus 4,500. Minus just is the direction and it's not important. So instead of the direction being down like this, it's going to be up or down or up, whatever positive negative is based on that sign convention that we talked about. Okay, so the absolute value is important. So that's 3,000. Now I said if the cross section is a solid 4 by 6. The area of this guy is 24. Look, formula is right here. 3/2 V over A. V max is 3,000. Area is 24. That comes out to 125 psi. Easy. You don't have to use what? VQ over IT. That would be waste of time. What if the cross section of this beam here shown is a solid circle? And by the way, remember that the maximum shear stress happens right here, right on the neutral axis. This tau max that I calculated refers to this. Similarly here, the tau max happens right on the neutral axis, right in the center. And it's equal to what? 4/3 V over A. Again, 4/3, V is 3,000. And the area is pi r squared. The radius is 2. We get a tau max of 318.3 psi. By the way, no relation here between, I'm not trying to compare rectangle to a circle. If I made this a square, then I could, make some analogy out of it, but that's not the case. It's just an example. So hopefully I'll come back with a video in a few minutes, hopefully. Not few minutes for you guys, few minutes for me. And I will show you how you would handle hollow sections, and then also unsymmetric cross section like a T shape. Okay, that's the next video. As always, thanks for watching and listening.